This video starts with an overview of external flow, then continue with parallel flow over flat plates. Nusselt number is introduced, then the description extends the analysis to laminar and turbulent flows over flat plates with and without an unheated starting length. When you finish studying this chapter, you should be able to distinguish between internal and external flows and evaluate heat transfer coefficients in external flow and heat transfer associated with flow over a flat plate for both laminar and turbulent flows. The local and average Nusselt numbers have the functional form as illustrated. It is a common practice to non-dimensionalize the heat transfer coefficient H with the Nusselt number. K is the thermal conductivity of the fluid, and Lc is the characteristic length. The experimental data for heat transfer is often represented conveniently with reasonable accuracy by a simple power law relation to the given form. M and N are constant exponents, and the value of the constant C depends on geometry and flow. Re is the Reynolds number. It is a dimensionless ratio that depends on the surface geometry, surface roughness, temperature, flow velocity, and fluid type. PR is the Prandtl number. It is a dimensionless parameter that describes the relative thickness of the velocity and the thermal boundary layers. The Reynolds number for an external flow is shown in equation 6.13. V is the upstream velocity equivalent to the free stream velocity for a flat plate. The fluid properties vary with temperature. Thus, to account for the variation of the properties with temperature, the fluid properties are evaluated at the film temperature defined in equation 7.6. Consider the parallel flow of a fluid over a flat plate of length L in the flow direction. The x-coordinate is measured along the plate surface from the leading edge in the flow direction. The fluid approaches the plate x direction with a uniform velocity v and fluid temperature T infinity. The flow in the velocity boundary layers starts as laminar. Suppose the plate is sufficiently long. In that case, the flow becomes turbulent at a distance of x critical from the leading edge, where the Reynolds number reaches its critical value for transition. The transition from laminar to turbulent flow depends on the surface geometry, surface roughness, upstream velocity, surface temperature, and the type of fluid, among other things, and is best characterized by the Reynolds number. The Reynolds number at a distance x from the leading edge of a flat plate is expressed in equation 7.10. Note that the value of the Reynolds number varies for a flat plate along with the flow, reaching the given form at the end of the plate. For flow over a flat plate, the transition from laminar to turbulent begins at about 100,000. Still, it does not become fully turbulent before the Reynolds number reaches much higher values, typically around 3 million. In engineering analysis, a generally accepted value for the critical Reynolds number is given in equation 711. The local Nusselt number at a location X for laminar flow over a flat plate was determined based on equation 719. From experiments, the corresponding relation for turbulent flow is given in equation 720. The variation of the boundary layer thickness is denoted as delta, and the friction and heat transfer coefficients along an isothermal flat plate are presented here. The local heat transfer coefficients are higher in turbulent flow than in laminar flow. The average Nusselt number over the entire plate for both laminar and turbulent are given in equations 721 and 722 respectively. It is desirable to have a single correlation that applies to all fluids, including liquid metals. By curve-fitting existing data, Churchill and Ozo proposed the following relation. These relations have been obtained for the case of isothermal surfaces. Still, they could also be used approximately for the possibility of non-isothermal characters by assuming the surface temperature to be constant at some average value. Also, the surfaces are considered smooth and the free stream is turbulent free. The effect of variable properties can be accounted for by evaluating all properties at the film temperature. Many practical applications involve surfaces with an unheated starting section of length z. Thus, there is no heat transfer between x equals 0 and x equals z. In such cases, the velocity boundary layer develops at the leading edge. Still, the thermal boundary layer starts to develop where heating starts when x equals z. Consider a flat plate whose heated section is maintained at a constant temperature for x equals z and beyond. Therefore, the local Nusselt numbers for both laminar and turbulent flows are determined based on equations 727 and 728, respectively. The resolution of the average Nusselt number for the heated section of a plate requires the integration of the local Nusselt number relations, which cannot be done analytically. Therefore, integrations must be done numerically. The results of numerical integrations have been correlated with the average convection coefficients, as illustrated in equations 729 and 730.